Siamo live. Però vedo un po' di gente che sta ora 5 minuti. Magari se la danno sta seduto di là. Tutto bene. Questo in particolare ieri mi è stato regalato, quindi vedete anche voi se sentite che passo, perché c'è una parte lo portate, non lo usate molto più di tipo, non più di metà perché spara tantissimo. Ieri abbiamo rimesso solo i microfoni portati,
non posso vedere senza canale, così penso sì, no, è bene.
So, good morning, everybody. Welcome to this new morning session. The first speaker of the session is Michele Rota. We'll talk about all photonic quantum teleportation and entanglement swapping using on-demand solid-state quantum emitters.
Can you hear me? Okay. Okay, welcome to my talk. I'm Michele Rata from Physics Department of Sapienza University of Rome, and today I will talk to you about my first 2 year of PhD, and in particular of the experimental implementation of the quantum teleportation and entanglement swapping protocols using on-demand solid-state quantum emitters. Just a little warning, this is not a theoretical talk, despite being a theoretical session, so I will show you some experimental data. Now, let's say we want to make a quantum network. Why not making it photonic? Which is, why don't we encode quantum bits in a polarization state of light? We have a lot of advantages. Photons are extremely resistant to decoherence. You can manipulate their polarization state with linear optics, namely linear polarizers and wave plates. And we have extremely good single photon detectors. We have one downside: photons tend to be absorbed by matter. You suffer from losses over long distances. Moreover, classical amplifiers are forbidden by the no-cloning theorem. But we have a solution. Building a quantum repeater, which is based on a peculiar quantum phenomenon, which is entanglement. What I'm talking about? I'm talking about implementing a quantum teleportation protocol, which is distributing a state over a distance, and an entanglement swapping protocol, which instead distributes entanglement over distant nodes. But let's first focus on what quantum teleportation is. Now, this is the basic scheme of quantum teleportation. The core of quantum teleportation is entanglement. Entanglement states that if we measure one part of an entangled state, this immediately affects the other part of the wave function. So, in first place, we will need a source of entangled photons. Then we have a photon we want to teleport. We will make a measure of the Bell state of photons 1 and 2. For those of you who are not acquainted with Bell states, I read them here. They are the 4 independent entangled states of 2 particle systems, and they are a complete base for the Hilbert space of 2 particles. Then we make this measure. The wave function of the other part of the entangled couple collapse. We need to send through a classical channel the result of our measurement. I'm sorry to tell you, this is not classic teleportation. There is no violation of causality. So through the classical channel, the receiver can apply a unitary transformation to the state and retrieve the same exact photon as the input state. Now, let's get more into the detail and write some equation. Now we can write the complete wave function of the 3 states as a direct product of the entangled couple, for example, in the phi class state, and the generic polarization state of a single photon. Now, since the Bell states are a complete basis, we can rewrite these changing labels, and we get this equation. Now, if we look carefully, when we make a Bell state measurement on photons 1 and 2, which is we measure one of these 4 possible outcomes, we collapse and for example, we get the psi minus state as a result. Then the wave function of the photon number 3 collapses into this particular state. Now we tell the receiver which unitary operation to do. In this case, it is a spin flip with phase changing, and we get the initial state at the end. Now, what is this Bell state measurement in practice? The core of the Bell state measurement for photons is a simply 50-50 bin splitter. We send undistinguishable photons at the entrance of this 50-50 bin splitter, and then we plot the correlation histogram of the exits at the two detectors of the output of the beam splitter versus the time tuning of the time of arrival. And we see that we have, if we send different bell states in the inputs, we have 4 different behaviors. In particular, there is one bell state which catch our eyes, psi minus. It is the only one which has a positive correlation, a peak in the at 0 detuning, so when the photons arrive at the same time. What does it mean? It means that if we get a double click on the detector, we're sure that we got psi minus measure. Now we go for the entanglement swapping. Now that we explained in details the teleportation, entanglement swapping is quite similar. We just add the photon. Now we have 2 sources of entangled photons, and the aim is to make a measure on the inner photons and swap the entanglement to the outer photons. So again, we write the 4-photon state. Now it's a direct product of 2 bell states. And again, by doing some magic mathematical trick, I can rewrite it in this particular choice of bell states, and where I couple the inner photons bell state and the outer photon bell state. Again, we see that if the bell state measurement gives us a psi minus measure, then we are sure that we projected on an entangled state the photons 1 and 4. In particular, with this choice, we project on the same bell state. I want to stress that photons 1 and 4 never saw each other, never interacted before. So this is the idea of entanglement swapping, to swap the entanglement between 2 couples out to 2 photons which were previously uncorrelated. Now, this is all theoretical talks. Was it done experimentally? Is it something which can be implemented? And the answer is yes. In the 90s, the quantum community was quite active. And in the end of 1997 and in the beginning of 1998, 2 groups almost at the same time came out with 2 papers on the experimental implementation of quantum teleportation. And at the end of 1998, same group produced the obvious consequence of the experimental quantum teleportation, which is implementation of entanglement swapping. Now, what is the difference with the experiment we performed? The source. In these cases, in the 90s, the source was spontaneous parametric down converters, which are a particular type of nonlinear crystals that under some conditions can emit entangled photons. But this source is intrinsically statistic, which is it does not work on demand. On-demand operation is something we want if we want to make a quantum network, quantum computing, quantum technologies. You want to push a button, get photons out. So what I'm telling you, is there a possibility to have a source of entangled photons which works like, I don't know, laser pointer, an entangled laser pointer? Well, our answer is yes, it can be done, and it can be based on quantum dots. This is an entangled light emitting diode. This is a pictorial image, which was implemented experimentally in 2010, and it's based, the core is quantum dots. What is a quantum dot? A quantum dot can be done by growing an island of a semiconductor with nanometric scale inside the host matrix of another semiconductor with higher bandwidth. What we get is an effectively zero-dimensional semiconductor nanostructure which confines the electron hole wave functions in all the 3 dimensions. This confinement produces, in the luminescence spectrum, in the emission of these structures, sharp lines which resemble nearly single atoms emission spectra. This feature gained the quantum dots the nickname of artificial atoms. Okay, but can we make entangled photon pairs with quantum dots? Yes, we can do it by exploiting the bi-exciton, which is 2 electron hole pairs excited at the same time in the quantum dot, and by exploiting the 2-photon cascade out of this quasi-particle, we can have the recombination of electron hole pairs and the emission of 2 consequently photons. Now, what I did not tell you is that the intermediate state, so the single exciton state, is actually doubly degenerate in the spin projection. So what we have is two radiative decay paths which can be followed. For example, first we can get a left circularly polarized photon, and then a right one, or vice versa, a right and a left photon. Now, if the paths are truly indistinguishable, then the state is entangled. And if you rewrite the wave function in the HV basis, we can see that the emission is in the phi glass bell state. Okay, we have the source. Why nobody tried it before? Well, in the end, I will show you some reasons why, which we discovered after performing the experiment. But the experiment for quantum teleportation, this is the experimental setup, schematic of the experimental setup. Okay, what we have here, we have an entangled pair emission source, which is gallium arsenide quantum dots, resonantly excited with a titanium sapphire pulsed laser, and this is the core of the on-demand operation. We can decide when to have photons, and the quantum dot emits entangled photon pairs at a 2 nanosecond repetition rate, every 2 nanoseconds. Then we have the state preparation, which is simply a linear polarizer and a lambda plate. We have our implementation of the Bell state measurement, tuned for the psi- state. And then we have the analysis of the teleported photon. We want to know which is the outcome of this teleportation. Was successful? I remind you that if you do not make a unitary operation, and this is the case, this is what comes out. So the coefficient for the polarization are swapped. So what do I expect? I expect an anti-correlation in polarization. So we measure the second order correlation between these two photons after we detected a psi- state, and we make co- and cross-polarized second order correlation, which means we measure same polarization and cross-polarization, and we see that at 0 time delay, we have more photons which comes. We can build the fidelity of the teleportation protocol, which is the percentage of good teleportation. Was it successful teleportation? And we show that this fidelity was above the classical limit in all possible bases, so we can say that quantum teleportation was successful. Now, entanglement swapping setup is quite the same, very similar. We still have our entangled pair emission. Then we have the Bell state, still selecting the psi- state. And now we need to check the two-photon state, if it's psi-. Now we need to reconstruct then the density matrix of this state. And this is the experimental result. We can confront it with the theoretical expectation, which is the psi- state, and we can build a fidelity to the psi- state, which tells the similarity between these two states. And we show that the fidelity is above the classical limit by 2 standard deviations. So we can say, yes, entanglement swapping is successful. So what did I show you to conclude? Is the first experimental implementation of quantum teleportation and entanglement swapping protocols using photons from quantum emitters, namely quantum dots. Okay, can we do better? Yes, you saw the results are not so high, the error is big. So we need perfect sources. In the way towards these perfect sources, we can make photons more indistinguishable, and we saw it was a requirement of the Bell state measurement. This would push up the fidelity value. This can be done using optical cavities and exploiting the parcel effect. We can also make photonic structure to increase collection efficiency. That matrix I show you is the result of one entire month of measure continuously. So, and the error can be decreased if we make something to squeeze photons out of the structure and increase the emission rate. Another cool thing to do would be to add an external perturbation like strain to tune the quantum dot emission in order to make it suitable for other quantum technologies like atomic vapor quantum memories. So this is the end of my talk. I would like to acknowledge all the people in the team where I work, in particular Francesco and Davide, which were with me for the entanglement swapping procedure in Rome. This is a joint experiment between the Rome group, JKU in Linz, Austria, and the KTH in Stockholm. In particular, I also want to thank Christian, which joined us for the entanglement swapping, Marcus for the teleportation, Simon drew the samples we used, and Armando supervised the work in Linz. I would like to thank my supervisor, Rinaldo, and last but not least, Klaus and Katarina, which came from the KTH Stockholm to help us doing the entanglement swapping experiment. With this, I end my talk, and I thank you.
Thank you, Michele. So now it's time for questions, comments. Nobody? Okay, I have a question. In the beginning, before introducing the entanglement, you showed that the psi minus state is positive, right?
What do you mean?
In the graphs, when you show...
Yes, the correlation, yes.
Can you explain the physical...
Yes, of course.
Yes.
So, I will explain it by showing you how the Bell states looks like. Okay, we can see that this Bell state are okay. We are dealing with photons, so in the end, the wave function must be symmetric. So there is two ways to make wave function symmetric. Either everything is symmetric, or you make two parts antisymmetric. And phi plus, psi plus, and phi minus are symmetric under the exchange of particles and symmetrics in the polarization. While psi minus is completely antisymmetric in both the spatial part and in the polarization part, which means that if we test the spatial part, so we send and make an interference in a beam splitter, the outcome must be antisymmetric. So the particles will go out of the beam splitter and cannot coalesce, they cannot stay at the same output. So this graph tells us that these three bed states, the two particles, the two photons comes out at the same output, while psi minus, which is antisymmetric in the spatial part, comes out one photon in one part and one photon in the other.
Thank you. If there are no more questions, comments, let's thank the speaker again. So the next speaker is Gaetano Luciano, who will talk about neutron mixing and oscillations in outer radiation in the proton testing.
So I'd like to thank the organizer for this opportunity. And well, basically, I want to tell you something about neutrino mixing and oscillations in connection with the Argo effect and in the context of the weak decay of accelerated protons. And this work has been realized in collaboration with Massimo Blasone, Gaetano Lambiase, and Luciano Petruzzello from University of Salerno. So that's the outline of my talk. Let me start by briefly introducing motivation and the basic tools useful for my analysis. I mean the Andrew effect and the mixing transformation for neutrinos. So, what is the Andrew effect? You know that from the point of view of a uniformly accelerated observer, the inertial vacuum is not completely empty, but it appears as a thermal buffer of particles with a temperature T that is proportional to the acceleration according to this equation. And this was shown by Harlow in 1976. And such an effect can be considered as the flat counterpart of the Hawking black hole radiation. Well, that's a pictorial interpretation of this effect. We have on the left the accelerated observer who feels warm in the inertial vacuum due to the thermal buffer of particles. And on the right, we have the inertial observer who is frozen at 0 Kelvin in his vacuum state. Okay. Well, the other tools are the mixing transformation for neutrinos. Let me say that in some sense neutrinos are magic particles since they can change their flavor during the space-time propagation, as you can see from this plot, where we have the oscillation probability versus the distance traveled by neutrinos in a simplified two-flavor description. And in order to explain this phenomenon, Pontecorvo in 1978 supposed that the states of neutrino with definite masses, μ1 and μ2, which are eigenstates of the Hamiltonian, so they are eigenstates of the time evolution, do not coincide with the eigenstates of the charge of the interaction, the A and the mu, but these two, in quantum mechanics, these two sets of states are simply rotated with respect to each other, okay, where theta is the mixing angle. So in quantum mechanics, the flavor and mass representation are completely equivalent since they are related by a simple rotation, okay? That is a unitary transformation. But in quantum field theory, that's no longer true, as it was shown in this paper. Indeed, if we implement the mixing transformation at level of field operators, both mass and flavor field operator, we get this expression for the vacuum annihilator in the flavor basis. So you can see that it is related to the corresponding ladder operator in the mass basis by means of two transformations. The standard Pontecorvo rotation and the Bogoliubov transformation, which is absent, of course, in quantum mechanics. Well, these are the Bogoliubov coefficients. They are given by products of spinors. And, well, it's possible to show that this Bogoliubov transformation is responsible for the unitary inequivalence between the two representations. Okay, so while in quantum mechanics we have two equivalent representations, in quantum field theory they are no longer true. Okay? Let me say that we have, for example, a similar situation in condensed matter system when we study a phase transition. We know that the phase of our system before and after the transition are different. They describe different physics. Okay? So, the problem is, which is the fundamental, the physical representation for mixed field, the mass or flavor representation, which are let me say the measurable states for neutrinos, the mass or flavor states. And well, there is a controversy in literature on this topic among people who support one position and people who support the opposite position. And I just quoted some of the most important references on this topic. Well, let me say that the clue to an answer to solve this question can be found in the study of the inverse beta decay of accelerated protons. Well, you know that a proton is a stable particle according to the prediction of the standard model, since its lifetime is higher than the current age, the present age of the universe. However, if we kick a proton, if we accelerate a proton, the situation is maybe completely different. In particular, if we supply the mass gap between the proton and neutron, in principle, this process may be not forbidden. So the proton can decay into a neutron, positron, and an electron neutrino. So we have the so-called inverse beta decay. And here we have a rough estimation of the proton lifetime for characteristic acceleration. For example, for A, on the order of the acceleration at LHC, we have a lifetime that is 10 to 3 times 10 to 8 years. So that's the reason why it is very, very difficult to see a proton decay at CERN. But the situation is completely different in astrophysical regime, for example, in proximity of a pulsar, where we have a lifetime that is much shorter. Okay, so this is the decay we have in the laboratory frame, in the inertial frame, where the particle is accelerated. But now the question is, what happens in the moving frame, where the proton is at rest? So in principle, it should not decay. Okay, but that's not the case. The proton decays also in the moving frame, thanks to the Arrow effect. Indeed, it's possible to show that the proton interacts with the thermal bath of electron and neutrinos, antineutrinos. So, these are the processes we have at the level. So the decay occurs also in the moving frame. Okay. Well, the first approach to the study of the inverse beta decay in QFT was made by Matsas in his work in 1999. In particular, the author considered the neutrino as a massless particle, so no mixing. He works in the approximation of small acceleration with respect to the mass of both neutron and proton, the so-called non-recoil approximation, and he describes the interactions by means of the current Fermi theory. So this is the action which describes the coupling between the accelerated nucleon current, J mu, and the corresponding electronic current. Okay. Well, let me skip technical details. We can discuss later if you are interested in these details. However, I just want to stress that if we compute the scalar decay rate of this process, that is the probability of decay over the nucleon proper time t, we get this expression in the laboratory frame where this is the Bessel function, and this is the corresponding expression in the moving frame, and it's possible to show that the two decay rates are equal, and this was exhibited as a theoretical proof of the necessity of the Arrow effect in QFT. Indeed, without the Arrow effect, the two decay rates would be different, thus violating the general covariance of QFT. Okay. Well, so far we have considered the neutrino as a particle with a definite mass, but we know that neutrinos are mixed because of flavor oscillation. So the question is, what happens if we try to embed mixing in this framework? And let me say that the first attempt to do this was made by Alvaria in his recent work, and in particular, the author argues that while in the laboratory frame, the interaction is the standard electroweak interaction, so neutrinos are produced in flavor states. In the moving frame, the proton interacts with the thermal bath of electron and neutrinos in regional states, which have an effective thermal weight, so they are produced in mass eigenstates. You also notice that if flavor eigenstates were used as asymptotic states also in the moving frame, then the thermal behavior of the Arrow effect will be violated. So he concludes that he works with mass eigenstates in the moving frame and flavor eigenstates in the laboratory frame, and he concludes that the two decay rates are in disagreement when neutrino mixing is taken into account. And such a contradiction can be solved experimentally. But of course, we cannot share such a result because by construction, the QFT is generally covariant. Also, the standard model of fundamental particle is generally covariant. So we approach the study of the problem looking for a solution which could be compatible with the general covariance of the theory. Okay. So let me say that we may be considering the paladins of general covariance of QFT. That's me, Dasone, Lambiase, and Pesuzzillo. Well, first, notice that in the presence of mixed fields, the Arrow effect loses, the Arrow distribution loses its thermal behavior, okay? And this correction arising from mixing appear at order higher than first in the M over M, where the M is the difference mass between neutrinos. So there is no prescription which imposes that the Arrow effect must be thermal even for mixed fields. So no prescription which imposes the use of mass eigenstates in the moving frame, unlike Alvaria's claim. And indeed, if we work with flavor neutrinos, both in the inertial and moving frame, the agreement between the two decay rates is restored. Indeed, this is the decay rate in the inertial frame. The structure is very clear. This contribution arises from N1 when we replace Ni as asymptotic states in the transition amplitude. This contribution arises from the two, and this is the contribution which arises from the coherent superposition from the interference between one and two. Okay. Well, this is the corresponding expression in the moving frame. The structure is the same. Now, the off-diagonal contribution has this later awkward expression. Okay. But if we compare the two decay rates, it's possible to show that these two terms are equal, these two contributions are equal. So the question is, what happens to the off-diagonal contribution? Are they equal or not? Well, calculations in this sense are non-trivial, as you can see maybe from this picture. However, if we work in the approximation of small mass difference between neutrinos, that is a realistic approximation, it's possible to show that the two decay rate, the two off-diagonal contribution are equal up to the leading order in the M over M. So the two decay rates are equal up to the leading order in the M over M. So it seems that flavor states are the physical states, since they are consistent with the general covariance of GFT. Actually, let me say that in this work, which was published in the same day of our contribution, it was shown that even mass eigenstates are consistent with the general covariance of quantum field theory. In particular, the author says that a physical Fock space for flavor neutrinos cannot be constructed, so these states, flavor states, are only phenomenological. Okay, so he works with mass eigenstates, and he shows that even in that case, the two decay rates are equal. But let me show why this setting, why mass eigenstates cannot be considered as physical states, even if they are compatible with the covariance of the theory. Well, first of all, it is not true that we cannot construct a physical Fock space for neutrinos or flavor neutrinos, as shown in this paper. Then it's possible to prove that if we work with mass eigenstates in the two frames, this is the expression of the decay rate we will obtain. That is the standard result as in the absence of mixing up to a cosine squared or a sine squared. So, as you can see, there is no signature of the interference term, no signature of the coherent superposition between the one and the two. So, there is no possibility to describe the phenomenologically observed flavor oscillation using mass eigenstates. So, that's the reason why these states cannot be considered as the physical state for neutrinos. On the other hand, let me show that flavor eigenstates are consistent even with the description of flavor oscillation. Well, this is the diagram, the process in the inertial frame without oscillation, and we commented above such a process. And this is the corresponding process if we take into account oscillation. We have an electron neutrino which oscillates in a muon neutrino. Okay. And in this case, the decay rate is proportional to cosine squared, sine squared, as expected, since this is a pure interference term. The total decay rate, which is the sum of these two contributions, takes this simple expression. Okay. Now, in the moving frame, that's the situation. These are the processes if we neglect oscillation, and these are the corresponding processes if we take into account oscillation. And the remarkable point is that if we want to preserve the covariance of the theory, we must require that the Unruh radiation, the Unruh thermal buff, is made up of oscillating neutrinos. So neutrino oscillation occurs also in the Unruh radiation. With such an assumption, that's the expression of the total decay rate, which is exactly the same result as in the inertial frame. Okay. So conclusion and future perspective. That's an overview of the various approaches used to the study of the inverse beta decay with mixed neutrinos. And I stress again that the only setting compatible both with the general covariance of GFT and the description of flavor oscillation is the one based on flavor states. So flavor states are the physical state for mixed neutrinos. Future perspective, well, as I told you, we worked in the approximation of small mass difference between mixed fields to the leading order in the M over M. So the question is, what happens beyond this approximation? There are two possible scenarios. On one hand, if the two decay rates are equal at any order, then the contradiction raised by Alvaria will be solved without involving experiments. On the other hand, it may happen that at some order, the two decay rates may be different. Okay, but this will be, in contradiction with the general covariance of GFT, but we cannot violate the covariance of GFT, which is our lighthouse. Let me say it's our lighthouse. So in this case, it is clear that something must be modified. For example, or we must take into account the non-thermal correction to the Arnold radiation, which did appear at order higher than first, or we must abandon the Pontecorvo treatment of mixing in favor of the full theoretical one. And well, then we want to extend this consideration to carbon background, since gravity effects may be non-trivial, as I told you in the introduction. And finally, we want to extend this consideration also to condensed matter system, exploiting the analogy between the BDG equation for superconductors and the Dirac equation or Majorana equation, if you. Okay, and that's all. Thank you.
Do you have any questions? No. I have one. So I was wondering what would happen if, in the case of CP violations. Have you considered this, or?
No, because well, in that case, of course, you should consider three generations. We didn't work with three generations, but we think that that's only a problem of calculation. I mean, the general covariance in this case should be preserved. Okay. We think that apart from these technical problems, all the apparatus, all the framework should be the same. Okay. So, well, I think that it's only a problem of calculation with the three generation. Okay. I think that there are no more complicated, no more conceptual complication. Okay.
Okay. Thank you. There are no more comments, questions. Let's thank the speaker again. The next speaker is Chiara Signorile, who will talk about factorization and local subtraction of infrared divergences for QCD processes.
Okay, thank you for the introduction and for giving me the opportunity to present my presentation. So the project that is done in collaboration with the Phenomenology group in Torino. And okay, so which is the natural environment for this project is another collider. That's because we can, in this very amazing laboratory, you can study proton-proton collision. That for a theoretician physics is something like that. Okay, we don't have to start panic because general theorems ensure that we can factorize the dependence on short distances from the one on long distances. And we are interested in the part depending on the hard subprocess, which is this red dot over there. Why? Because in this region we have a very small parameter that we can use to make perturbation theory. And in particular, if we assume that only quarks and gluon are involved, we can use perturbative QCD, where perturbative QCD is a quantum field theory with an unbroken SU3 non-abelian gauge invariance, and it describes the interaction between quarks and gluon. Why we use this theory? Because it has a really amazing behavior in high energy. Because it is asymptotically free, and that is because its coupling constant decreases as long as the energy increases. And in this regime, we have this small parameter to use to expand our observable powers of this parameter. Just think about a Taylor expansion. In this regime, the quark masses are negligible, and therefore two different kinds of divergences arise. One is when this gluon became soft, meaning that its energies goes to zero, and the other configuration is when this gluon became collinear to this particle here, this quark. If we think about the covariant approach, we know that this intermediate particle in these two kinds of configuration is on its mass shell, meaning that it's a real packet that can propagate indefinitely before the emission. So there is this theorem that ensures that these infrared divergences coming from two different contributions at the same perturbative order cancel order by order in perturbation theory. If we take, for example, this very simple process, a plus and minus into cuckoo bar, we see that at the next reading order, let's say at the second order of our Taylor expansion, we have two different contributions. One is the real contribution, where we have an extra gluon in the final state, and the other one is when this gluon makes a loop. So the divergence is coming from this term, and the divergence is coming from this term, cancelling the sum. Okay, so the problem is that if the sum of these two objects is finite, why we should deal with a subtraction method? Well, in principle, it's not necessary, but in practice, is. Because these objects here are really, really complicated, and therefore we need to compute them with numerical tools. We cannot compute them analytically, and therefore we need to handle with finite quantity in each stage of the computation. So therefore, we need a subtraction method, meaning that we want to make the real contribution finite before performing the phase space integration. And this can be done by adding and subtracting a counter term. This counter term is an object that has the same singular limit as the real matrix element, but is simple enough to be integrated analytically. And therefore, we have this observable. We know that two terms contribute at the next reading order, the virtual one and the real one. We subtract to the real one its divergent configuration, and we know that this term here is now finite. But then we have to add it back, otherwise we are modifying our observable, and we can do it using this, its integrated version, I, which is the integral of the counter term in the relative phase space. Okay. In this way, we can reproduce the poles, the divergences that we had before adding and subtracting the counter term. Okay, the construction of a counter term is not an easy job because we really need a lot of ingredients to construct this object in a smart way. So first of all, we need to recognize the fundamental limit that provide these divergences. And they are the soft and the collinear configurations, as I showed you before. And in this case, we have in mind a very specific definition for these limits. We are taking the leading terms of this operator here, when all the four components of the momentum Ki go to 0. In a similar fashion, when we talk about collinear limit, we are taking the leading term of the observable O when K-perp go to 0, where K-perp identified the distance between these two vectors from a collinear direction. It's a way to describe it properly. Then we have to understand the structure of the real matrix element under these limits. And we see that we know from the literature that in these cases, the real matrix element factorizes into two parts. One is a universal kernel, this object here and here. We have an equal kernel here in the soft limit, and an Antarelli-Parisi splitting function in the collinear limit. And then we have a Born matrix element that depends on a kinematics, which is, not so comfortable, let's say. Because mass shell condition and momentum conservation are very just in the limit. Moreover, we want to split the phase space into sectors. This is a very useful thing to do because we cannot study all the possible singular configuration at the same time. By splitting the phase space in sector, we can focus on just a small amount of singularities in each sector. Obviously, when we sum over all the possible sectors, we have to recover the entire space. And that's why we require the sum to the unity of this sector. The last ingredient is a momentum mapping. I showed you before that the kinematics is not in all the possible points of the space on the mass shell and is not conserved. With a momentum mapping, we are able to move from a set of n+1 momenta to a set of just n momenta. But these n momenta are always on their mass shell and they are conserved in the vertices. So now we have all the ingredients, so we can define our counter term. We choose a sector. We know that these are the configuration contributing to the sector, and now we can just subtract to the real matrix element the singular configuration. So the soft one, the collinear one, and then here you can see a way to avoid a double counting, because we have configurations which are single, soft, configurations which are collinear, but we have also, let's say, a region where we have both the soft and the collinear configuration. And in the end, we use the mapped kinematic. So, this is just to show you that when we sum over all the possible sectors, we recover a very simple object here, where no more sector function appear, because they sum to unit, as I showed you before. So in the end, the integration of the relative space of this guy here is not so complicated, and we can do it analytically. So this is done the first part of the talk. Now I would just like to show you how we can recover the same result from a very general perspective, the factorization approach. So in this part, the idea is not to make finite the real matrix element, but the virtual one. And we can do it again, adding and subtracting a counter term, which in this case can be found by using a completeness relation. So we know that an amplitude, a massless amplitude virtual, can be split in this kind of structure, where in this case we see that we have just a universal function that describes different kind of configuration. With this fraction here, we are able to recover all the purely hard content of the amplitude, while with this soft function, we can describe all its soft and soft collinear content. These functions are universal and gauge invariant, and they are defined at all orders in perturbation theory. But this function has also another interesting property. They are related to their radiative counterpart, meaning that we know from the formula that I just showed you that the virtual contribution can be written like this, and each of these functions is related to a radiative counterpart. Here we have just a picture. And this property is valid at all orders in perturbation theory. So we know that the virtual part is written through this function. We know that they are related to a radiative counterpart. And in this way, we have a natural candidate for a counter term. And that's exactly what happened. So in this way, we want to make this part finite. We can, using the relation I showed you before, define this object here, and then its integrand k. And here we have the explicit form. And if we compute this function here, we recover exactly what we found before. And here comes my conclusion. We have investigated the infrared divergences, and we have understand how a cancellation occurs when we sum the virtual and the real matrix element. And we provide a method to subtract infrared divergences in a very local, analytical, and efficient way. Thank you.
So, do you have questions, comments, curiosity? No? I have one. So, is it possible to go further in the perturbation theory?
Yes, exactly. We have already produced some results, but next to the order, the pattern is extremely more complicated. So we need more counter terms. The structure is really more involved, but we can do it in both the approaches.
In both approaches?
Yes.
Thank you.
Exactly.
So if there are no more questions, let's thank the speaker again. The next speaker is Michele Zuccotti, who will talk about machine learning and optimal navigation in complex flows.
So good morning, everybody. I am Michele Zuccotti from this university. So I am a researcher in this university where I work in the group of Biferale, where we mostly study fluid dynamics with statistical mechanics theoretical approach. And today, what I'm going to talk about is something different that we have started to do quite recently, the last years. And this is, as you can see from the title, is that we are trying to use artificial intelligence algorithms to develop smart swimmers that are able to accomplish complex tasks in complex flows. What does it mean complex tasks? Is that what the kind of swimmers we have in mind are not like big airplanes that they can just, if they want to go from point A to B, they just need to turn on their engine and go there, or maybe a big boat that if it wants to keep a position in the ocean, it just has to release his anchor. But we want to imagine swimmers that have a limited set of actions that they can perform, and that they always need to exploit the underlying flows to reach the target that they have to reach, their goal. And in particular for complex flows, we imagine that we have really turbulent flows that are characterized by a wide range of dynamics, which is covered by a wide range of scales, so different vortices of different sizes. So why we want to do this? We have actually, we were inspired by different applications. Some of them comes from medicine, for example. Here we are in the range of microfluidics, but here we can, here the problem is that the probes needs to be very small, and so they have really limited action that they can perform. But there are, as we can see in the literature already, even though these things are very difficult to build from an engineering point of view, there are already papers that start to think about this. And for example, this would be important for telemetry or for sensing. In some sense, if you want to put a sensor in a part of our body, we just not need only to send the sensor there, but we also need that to be able to stay in the position. Another thing that we can imagine is the drug delivery, for example. If we want to put a drug somewhere in our body without producing all the rest of our cells, we need to be able to send a drifter there and then be able to release the drug with extreme precision. So these are some application that comes from microfluidics medicine, but there are many others also from geophysical flows, for example. Here we took inspiration from this Lagrangian drifter laboratory that in California, they are already sending drifters everywhere in the ocean, as we can see from this map. So there are already hundreds of drifters that are extremely simple buoy, actually, that they can still perform a very simple action to control the position, but they cannot, they do not have an engine. And what they want to do, for example, here is that they want to have the maximum coverage of the ocean, and they want to avoid this kind of situations where this drifter gets stuck on the coast. Of course, it's not useful. Another thing that is very important is, for example, for them is to maintain the position in a place, because if they want to compare measurements on site from this drifter with the measurements from satellites, for example, it is important to have them on the same position every time, and this is extremely difficult. Another thing that the people are already starting to think about and that we also want to try to do, is that to think about collective behaviors of particles that all together try to reach a goal. For example, to track back the source of emitting pollution, for example. So out of all these interesting applications, let's try to see what is the problem that we have in mind to start. And this is a quite well-posed problem also from a mathematical point of view. It is called the Zermelo problem. And the idea is that we want to minimize the time of the trajectory of a boat starting from point A to point B. So the problem is quite simple. We have a two-dimensional flow, which is not time-dependent, and we have a boat that has to go from point A to point B. Of course, if this boat is a pure tracer, so its equation of motion is just its velocity is just equal to the velocity of the underlying flow. This is a problem that will never be possible to solve, because the boat will just follow the streamline of the underlying flow, and so it will never be able to go there. So what we have to imagine is that we have to consider this kind of equation of motion. So we have the velocity of the boat is given by the advection of the flow, plus another term, which is given by the velocity of the boat. This is the swimming velocity, which is constant for us. So this is a constant velocity. And then we have the angle of navigation. And the angle of navigation is the only thing we can control. And out of this, we want to understand how to change this angle to go from point A to point B. As I said, this is a mathematical problem that it has also an analytical solution, but this analytical solution is quite fragile in some sense, because it is chaotic, first of all. So if we change a little bit the initial condition, this will not only not be the optimal time to the target trajectory, but it actually will drive us completely to a different position. So it cannot be actually really used from a practical point of view. So what we want to do, we want to try to solve this problem with a different approach, which comes from reinforcement learning, which is a specific tool of machine learning. And we want to try to see how we can define the angle of navigation to have the best, the minimum time trajectory. To do that, we have, if you want to see a bit, it's the keywords are reinforcement learning, the policy gradient method. The idea, just to give you a sketch of what we want to do, is this. It can be summarized with this diagram. So we have an agent, which in our case is the boat, is our swimmer. We have an environment, which is the flow. And then what we need to do, of course, as we said, we need that the agent is able to take an action, which in our case is the angle of navigation. Then it has to be, the swimmer has to be able to measure a state where it is. So it has to measure what the action that chooses, if the action that it has chosen is brought in a state which is closer or farther from its goal. And then, in case it is closer to its goal, it has to be able to get a reward, which is good, which is a high reward. If its action brought in far from its goal, so the state is even farther from its final position, from its final goal, the reward will be very negative. And the core of all this approach is in defining a policy which tells us, which is a probability. It's something very simple. It's a probability which, condition to the state where we are, tells us what is the best action that we have to choose in order to reach our goal. This is the point. How do we do this? This policy is a distribution function which can be parameterized with some parameters, some weights, that can be updated during the learning procedure, which is following this stochastic gradient ascent technique. Which means the idea is simply that we want to maximize the gradient of this function with respect to the weights, proportionally in a way that we maximize the reward that we get at the end of our trajectory. Let's try to make this idea consistent with what is our problem. So here we have our environment, as we said, is a flow. This is exactly the two-dimensional snapshot that we took, stationary in time. And as we see, this is fully turbulent. So we have a wide range of scales in the dynamics that are involved if you look at the energy spectra. And then we have that, so we need to define a state, because we want to go from point A to point B. The state in our case is the position, and we have to perform this tiling of the space, that is this white square. So the particle is able to measure where it is with respect to this tile. Then we have our actions that we have taken as with the tile, as we said, the angles of navigation, and we have discretized them in these 8 possible directions, so north, south, east, west, and the 4 intermediate directions. So this is only the discrete set of actions that we can take, and these are the discrete states that on the position of the particle that we can measure. So because our goal is to go from point A to point B in the minimum time, the reward that we have made, that we have used, is a reward which is proportional to the total time that the particle spent to go along this navigation from point A to point B. So every time the particle moves, we add a minus delta t in the reward. So in the end, the total reward will be minus the total time. So the shorter is the time, the higher is the reward. The last thing that we need to define is the policy that we used. And the policy is, now without going too much into the details, but the policy is defined as a softmax distribution that has this shape here. And the property of this policy is that it is always a probability. It gives us a probability in each state to select the best action. So indeed, once we are in a state, we fix as I. Here we see that this is a probability which is a number between 0 and 1, which tells us what is the probability of the action AJ to be selected. And indeed, it is always normalized over all the possible actions that we have at each state. So once the policy will be trained, this policy will tell us, so we will have changed according to the stochastic descent, these weights, and this policy will tell us what is the action which has the best probability of being selected out of these 8 angles. Of course, this is always a probability, so there is also a little bit of stochasticity every time you select an action. It's not always one. Also, I mean, unless the policy becomes really a delta-like, we always have a little bit of stochasticity, and the swimmer can always have different actions in different states, even though the best action will have the higher probability. Let's try to see what happens during a learning process. So here we have the episodes. For the episodes, I mean all trajectories. So once we see the particle in the initial position, we let it evolve until it reaches the target. And so one trajectory from point A to point B is one episode. And then what we see here, we have the number of episodes, the number of times we sent this trajectory from point A to point B as a function of the total reward during the learning. So here we keep updating our policy. And what we see that at the beginning, the total reward, so the time spent from going to A to B is quite large. The reward is very negative. And indeed, if we take the policy at this point, after 200 episodes, we see that actually the probability distribution of the arrival time, which is also reflected on, it's not well picked, and it is quite broad here, and there are many trajectory that cannot even reach the target, and indeed this is visible from this cartoon of the trajectory, where we see that actually many particles are wandering in the fluid before reaching the target. Then if we keep going with the training, we see that our policy will improve. We will reach a higher reward, and indeed if we do again the same check, we start to run with this policy many trajectories. We see that actually now the PDF of arrival time is much more peaked. There are less failures, so less time now it happens that the particle cannot reach the target also after a very long time. And actually, if we visualize some of the trajectories, we see that they become more coherent and more quick going to the target. When the policy then converges, we see that the error reaches its minimum time trajectory, then we see that the error becomes constant, and indeed we see that the PDF becomes very peaked. There are no failures anymore, and indeed all of the trajectory that we are visualizing here in red goes to very coherently to the target. What is interesting is to compare the optimal policy. So after the policy has converged for different velocities of the boat. Indeed, here I was measuring a velocity of the boat, which is 40% of the velocity of the maximum velocity of the underlying flow. Because as I said, we don't want to imagine a particle that goes very fast and they can just go straight from here to here very simply. But it has a velocity which is always less than the flow. If we compare the results of the optimal policy for different velocities, indeed, we see that in here we have different velocities and different trajectories, because also we don't want to end up in a situation which is particularly just influenced by some strange trajectory. We tried many different trajectories, and what we have seen is that actually when the velocity is almost of the boat is almost one of the maximum, so it's almost the maximum velocity of the underlying flow, the trajectory looks a little bit maybe also trivial, quite straight, even though it's not really straight. While when the velocity decreases, we really see that the reinforcement learning is really able to learn how to use the presence of these big vortices to be accelerated and to reach the final target. What I want to show you here in this last slide is that actually this is not a trivial result, because we have compared the policies that it has been learned by the reinforcement learning with the trivial policy. For trivial policy, I mean that the bot is always able to navigate in the direction of the target, wherever it is. So we imagine that we can see the target where it is, so we don't care about the underlying flow, we just want to drive our bot in the direction of the target. So this would be a trivial policy that we don't need to learn in some sense if we can see the target, and we want to try to use this. And what we have seen here is that this policy, the trivial policy, can still allow us to reach the target if the velocity of the ship is almost equal to the maximum velocity of the underlying flow, but this is not optimal at all. Indeed, the PDF of the arrival time is larger, is wider, and is also picked at a larger value compared to the optimal policy. But the situation gets even worse when the ship velocity decreases. Indeed, not only the trivial policy is lower, but sometimes it can get stuck. It can get stuck into a big vortex, and so the particle is never able to reach the final goal. And indeed, all of them here they have failed. Now, to conclude, let's say I would like to conclude more with questions and with statements, because this is a new work, and this is also something that we are interested in keep working in the next years. And what we would like to do is now to try to apply our final goal. What is that we want to try to use this kind of techniques, which looks promising up to now, in this simple test case that we have used, to try to answer more complicated questions that have also theoretical interest. For example, like, can we use this kind of technique to learn what are the regions in space, in a flow, that are more important to measure from a data assimilation point of view? So can we be able to learn, to teach to particles to go somewhere that if we know about the fluid properties there, we can reconstruct the full field in a better way than if we have measurements in a random way. Even more optimistic, what we would like to understand is, once we know how to control this particle, can we also be able to make them react to the flow and then control the flow properties? So this is, of course, different, it's more complicated questions that anyway we will try to answer in the next years, at least. Thanks.
Is there any question?
Thank you for the response. Just one technical question. When you were training, when you were changing the position of target in every episode?
No. The training, well, we were. It's yeah, from here, for example. The training is always concerned to one trajectory, but still there is not a precise point to start. So we have a noise. So we have this area where the particle is initialized. So we measure that we do not know the initial position of the ship exactly, and this is something that for sure will break the optimal the analytical solution, because the analytical solution is chaotic. So we select an area from where the particle can start, and then we give a radius around the area that we want to reach. But then once we have selected this area and the target area, then along the training it is fixed. So we don't
one episode is fixed, or
no, in the full training is fixed. So all the episodes start and we want to reach that position with an error. It's all.
And just another question, maybe you said I missed. Is the gamma 0, the distance factor?
It's gamma is 1 in this case, because we have episodic case, so the total reward is always
Instant.
So let's say this total reward is this reward. Once the particle reaches the target, it's limited, so it cannot continue. The episode will stop. It's not a continuing case where you need the discount factor gamma to have a finite reward. Here, in this case, we always kill the episode at some point, either if we reach the trajectory or if it was for too long time. At some point, we kill it, and it will receive a very negative reward, which is given by the fact that the time that is spent in the trajectory is very long. But because we have this episodic case, we do not need to define. We use just for simplicity gamma equal to 1, and this is actually even more correct, I think, because it means really that you are improving your policy, maximizing your gradients as a function of the total time. So which is what we want.
Other questions?
Thanks for the talk. I was asking myself, is there any way you can check if you're on true minimum time or you're not stuck in local minimum?
Right, that's a difficult thing to check when you have this kind of problems with stochastic gradient methods. I mean, what we did for the moment is that we performed many different learning results to see if actually the policies was converging always in the same trajectory, and this is what we found. Because probably anyway, I mean, there is some noise. I mean, there is some stochasticity in the action, the selection of the action. So probably, I mean, there is not. I think it's not easy to prove that we do not fall into a local minimum. But what we have seen, at least from our simulation, is that all of them goes to the same minimum. So which maybe one can imagine is also the minimum, the global minimum.
Okay, thank you.
Hey, just a question. Did you try more directions to see how that would affect and speed up the training process, or?
More direction, what do you mean?
So like you have 8 possibilities, right? When you move north, south, east, west.
No, that we didn't try. Yes, that would be interesting. Yes, we can try.
Yeah.
For the moment, we took these 8 actions. Yes.
And then did you is there like so if you have a uniform distribution of probabilities, so you have 8 possibilities.
Mm-hmm.
So you got to some point where if the probability of one direction is not so much higher than another, do you still take it, or do you have? Is there a minimum probability that you need between the two? So you have like 2 possible.
No, that's
yes or no.
That's we see that it depends. So that depends on the training stage. So at the beginning, all the actions they have the same probability, and so it's just that we just selected select in a random way in this case the probability, and then while the policy is updating, we will have some probability, some action that will become more probable. But otherwise, we will always select an action with its probability. We don't have any other, let's say, limit that we put in. So it's really it's a softmax as it is defined.
Yeah, but if one direction is not so much more probable than another,
then we will take some time in this action, and many other times also the other action which has more or less the same probability, depending on it's. And anyway, what we have seen is that once the policy is trained in the region that is close to the optimal trajectory, the action has a quite peaked probability. So there is a best action which is identified, and the probability of being selected is very high. But there are then also maybe other regions. If you fall for a particular case, I mean, in a lucky way, you fall in a regional space that is not really trained, you still have this problem. But this is part of this policy gradient method, where you don't want to be greedy. You always want to have a probability of exploring your action space.
Okay, so let's thank Miguel again. And move to the next part of the session, which will be given by Tommaso Alberti, who will talk about the Pullman's magneto-hydrodynamic equations, a discrete dynamical system.
Okay. Thank you to the organizer for this conference, and I will show you some, I think, beautiful results about different approach on the magneto-hydrodynamic equations by using a simple approaches in this topic. And I will show you, I will give you some words about the turbulence, and then I will move on the relationship between turbulence and dynamical system, moving from Frisch to my work. As you probably know, turbulence is a natural phenomenon, which is a beautiful phenomenon unless you are in a plane, which is generally an irregular motion characterized by chaotic behavior, random variations in space and time, like you can see here, and can be also seen as a chaotic solution of the Navier-Stokes equation. And this is the link between turbulence and dynamical system approaches I will investigate. And first works on turbulence started with Leonardo's experimental point of view, but they arrive at one main point by the work of Osborne Reynolds, who firstly noted that the properties of a dynamics of a fluid depends only by a combination of three different parameters, which form the so-called Reynolds number, from which the dynamic depends, and which is the control parameters of your fluid dynamics. Moving from lower Reynolds number to higher Reynolds number, we move from a laminar to a turbulent flow. And this is the control parameter. And the control parameter is important in dynamical systems. And I will show you later, our system is depending on this parameter. And this is the control parameter of our equation. And, sorry. As I said before, you need to keep in mind that turbulence cannot describe as a low-dimensional dynamical system, which is unpredictable, which means that you have randomness in space and time, so stochastic dynamics, and moreover, it would be the results of nonlinear interaction between different components at different time scales. And this is the idea of Richardson in 1922 with the famous Richardson cascade, from which you have to transfer energy from larger to shorter scales. And generally, when studying plasmas, and in particular space plasmas, we noted that they are highly turbulent and they manifest multi-scale fluctuation over a different range of scales with three different peculiar characteristic ranges. A large scale forcing range with a spectral slope -1, an inertial range which follows the so-called Kolmogorov theory in 1941, and a kinetic range, a sub-ion range on higher frequencies. And this is important because this results is plotted here in terms of frequencies, but the main idea about the cascade, which is something like that, is in K, in space and not in time. But this is interesting because it could open new perspectives and new points of view in this framework. And why link turbulence and dynamical system? Because by using the dynamical system approach, we can derive a simple rule, a simple mathematical rule, which allows us to describe the time evolution of a phase space state variable, if you want. And according to the shape, according to the mathematical definition of this function, according your variable is continuous or discrete, you can have continuous dynamical system of discrete map. But the most important thing is that if you look at the behavior of this function, you obtain interesting properties. One of these is that generally a system can be defined as linear or nonlinear according to the dependence of the state variable of the function f, which depends on these parameters, which are called bifurcation parameters. As I said before, the Reynolds number is a bifurcation parameter, is a control parameter for a system, for a fluid system. So approaching the study of turbulence by the dynamical system theory could be helpful to investigate the different dynamical regimes by changing these parameters. And another important thing is the existence of the so-called fixed points, which could be stable or unstable, which are important because your system can move towards these fixed points if the fixed point is stable, or can be rejected out from these fixed points, for example here, if your fixed point is unstable. And as you know, and as you can see here, the fixed points is only derived by looking at the properties of the mathematical view you choose to investigate your dynamical system. And another interesting thing is this. The main problem when you approach turbulence is that you have an equation to describe turbulence, which is the Navier-Stokes equation, for example, in fluid approximation. And as Laplace said, if someone knows a precise location of a particle and you have a mathematical tool, you can predict the behavior in the future. But the problem is that, as I said before, turbulence must be unpredictable and chaotic. So we deal with a problem in which we have a deterministic equation, but the behavior is completely chaotic, which is the so-called deterministic chaos by Poincaré in 1880. So this means that although we have a deterministic equation for the evolution, changing the control parameter could lead different dynamical evolution. This is the case of turbulence, and this is the case of the work I will show you. The first approach, simple approach in describing turbulent features by using dynamical system was made by Frisch in 1995, in which he simply rewrite the Navier-Stokes equation for incompressible fluids in this way by discretizing the time dependence and by completely neglecting the space dependence. And he named this particular map as the Pullman Navier-Stokes equation because it is interesting. Why? Because it is nonlinear, as required for turbulent phenomena, because we need to have a nonlinear interaction. It has a stochastic behavior like in turbulent flows. It is not predictable because it has a sensible dependence to the initial condition, to the initial choice of these particular parameters. But the main problem is that this is not strictly chaotic due to its dimension because it's one-dimensional. Moreover, it is one-dimensional, so there is no use for turbulence, which generally leads to 2D or 3-dimensional systems. And moreover, it is fluid. So if you want to approach the description of plasmas, you cannot use fluid approximation, but a fluid-like approximation. And the fluid-like approximation is the MHD approximation, the magneto-hydrodynamic description of plasmas, in which the equation are this one. You have nonlinear terms in the equation for the velocity field. You have dissipative term is both the equation for the velocity and for the magnetic field. You have a pressure term, and you have obviously the dimensionless field for study the uncompressible case. The main problem here is that if you are heavily neglecting this red term, which is a pressure gradient, the two equations become symmetric. And one way is to use the Leray operator, which is extensively used in fluid dynamics, which has a lot of beautiful properties. And the most interesting is this one, because applying the Leray operator to a gradient of a field, of a scalar field, you have that this gradient is 0. So you can apply this operator to our equation. You can write it assuming dimensional variables, and by determining these dimensional equations, you know that they are quite beautiful in a symmetric way, and they depend on the fluid and magnetic Reynolds number. And this means that the description of this equation can be made by changing the behaviors controlled by these two parameters, as Osborne-Reynolds said in 18th century. But the main problem is how to solve this beautiful equation, because here we have a time and a space dependence. A first approximation like that followed by Frisch is to use the Galerkin-Fourier approximation, and in this way you can separate the time dependence from the spatial dependence. And by choosing in suppressing all k wave vector except then one, you can look at a particular fixed scale by following the so-called Euclidean approaches. And this approach is quite similar to one famous paper in meteorology and weather prediction, which is the Lorentz paper in 1963 from the so-called butterfly effect for chaotic systems. And by using this decomposition for our equation, this is an example for the first component of the velocity field. You have that the three different terms can be written in this way, and by some algebra, you can derive the so-called, what we call Pullman's magneto-hydrodynamic equations, which are quite interesting because they depend on different parameters, beta I, alpha I, and gamma ij. These parameters are 12 parameters and can be seen as bifurcation parameters of our system, so control parameters. The beta I and alpha I parameters depend on the fluid and magnetic Reynolds number, so these are the main parameters controlling the evolution of the system, and why the gamma parameters are related to the interaction between spatial components, which now we suppress the spatial component, but we have a coupling between the different velocity and magnetic components, and they can be written as a third order tensor. And by looking at these equations, which in a similar form has been found by Carbone and Bentley in 1992 for a particular two-dimensional case, we know that the equations are logistic, like the work by Frisch. Moreover, we have dissipative terms which are parametric, so we can control the dissipation of the two different fields. Moreover, the system is chaotic because the dimension is 6. So by definition, the system is chaotic. And moreover, we have quadratic terms. This means that the system is nonlinear. So we have a nonlinear chaotic system, which is quite good for describing turbulent features. And moreover, in the ideal MHD case, when dissipation is neglected, the total energy is conserved, and the chaotic nature of the system is confirmed by looking at the Lyapunov exponent, where at least one is positive. And moreover, the system is dissipative because the phase space is contracting. We recover also some classical results. If we look at the one-dimensional case, by some algebra, we derived this equation, which is quite similar to that derived by Frisch. This is a generalization, if you look, of the Frisch equation. Moreover, we know that the equation admits a fluid fixed point by setting the magnetic field equal to 0. We have this evolution, which is stable, as also shown in Bohr et al. Moreover, we also found the arithmetic fixed point, which is important for plasma because this allows to describe two perturbations, arithmetic perturbation with correlation between magnetic field and velocity field, moving in the opposite directions, and which is stable only when the dissipation parameters are equals. And moreover, another one is the Taylor force-free solution, which allows us to derive a relationship between the different magnetic field components, which is not linear. And this is important because Taylor force-free solutions are found in nature. For example, you describe coronal loops, but also the field line currents in the ionosphere. But the most interesting case has two numerical cases. One is by setting laminar conditions, I call it, because the Reynolds number are quite small because our parameters are less than 1. We know a chaotic self-similar behavior, and by looking at the Fourier spectral energy, we know that there is only one spectral slot, which is a flicker noise spectrum, and which is peculiar of long-range single point-to-time correlation observed in plasmas, and this is a reflection of the scale invariant features. And this is important because plasmas are scale invariant, and the Kolmogorov theory is also based on scale invariant processes. But when the bifurcation parameters are changed, and in particular when moving towards larger Reynolds number, we again know the time series manifests a chaotic self-similar behavior, but by looking at the power spectral densities, we know that there is an emergence of another scaling regimes, which is this one, whose spectral exponent is -5 to the 3rd, which is likely related to the Kolmogorov spectral exponent, although here we don't have a scale dependence. Moreover, this can be interpreted as the occurrence of a saddle node bifurcation, and this means that the control parameters, in this case the beta high and alpha high, or the Reynolds number, control the autocorrelation function. This means that control the memory effects in the system. And these results I call a turbulent plasma, because if I were, for example, Reynolds, I would be very happy to obtain these results. Also, if I were, for example, Ruel and Teges, I would be very happy to obtain this result, because this is the proof that the off bifurcation is not the mechanism generating turbulence, but the saddle node bifurcation. But in a Kolmogorov point of view, this is quite good because the evolution of a particular mode is important for investigating turbulent features, not only the scaling properties. And moving to my conclusion, the most interesting thing is that bifurcations in plasmas can be simply described by a 6-dimensional map depending on 12 bifurcation parameters, which admits all usual fixed points from the fluid to the Arfmanic fixed points. And the most interesting feature is that bifurcations occur with two spectral regimes characterized by different scaling spectral exponents, which are quite similar to those observed in real plasmas. And we are now investigating how bifurcation parameters are able in controlling the memory effects, and moreover also to derive a multifractal description to investigate the intermittency nature of fluctuation, because this is in time. So we have to investigate how intermittency can be described as a process in time and not in space. And I need to stop. Thank you for the attention.
Are there questions?
Thanks for the talk. In slide 9, can you thank. Well, what do you mean by stochastic behavior? I mean, it's similar to stochastic behavior, or noise, right?
No, because I don't show here the other figures shown by Frisch, but they investigate the stochasticity present in this time series according to the different evolution. Yes, these look like noise, but these look like the logistic equation, logistic map, which has the quite similar form, and this means that you have a stochastic distribution of your field. In this case, you have a one-dimensional field, so yes, it is quite difficult.
I mean, you don't work with noise. It's all it's chaotic, but not by deterministic. I mean,
yes, in this case, yes, there is no noise. Yes, in this case, no.
You do not model your.
No.
Okay.
No.
Thanks.
More questions, comments? If not, let's thank the speaker again. And now we'll have the coffee break.
Do you have a USB? Yes. Okay, can I forward to the Yes, Okay, so è la nostra scarica. YRM, yes. And then you check how it looks. Yes. Take confidence with the controller as well. Yeah, this is yeah. If you need, I can set it for you. So yeah, okay. Down it goes forward. And yeah, it's a bit reversed. Yeah.
And there's a laser pointer with this one? Ah, yes, so it's button.
Perfect.
Thank you very much. Should I leave it like this or?
Yes, you're the first one, right?
Yes.
Oh, no, you're the second one. The first one is Daniele.
Ah,
So,
okay, sorry.
Let's,
Then,
the
yes,
presentation is already here. Yes.
I thought that was but
No. You are the second one after Daniele.
okay. Thank you. Okay, thank you very much.
Ha fatto un po', sì, c'è delle buone. Ci hanno messo io. Quando c'è qua questi sono tutte di questi saranno la prossima sessione, però la metto session, no, ci sta session 4 materia, session 5 physics, session 6 physics. Windows scusa, se non sai sesta mazzettici di ieri nel cestino, non stai a stare allora. Scusa, guarda il 4, non può essere cittadino, ma ci sono mazzettici di Windows. Session 5 su physics, session 6 physics, un pezzo di physics. Magari in alto a destra.
No, stare Scusami, ma le presentazioni della sessione di questa mattina le avete già tolte?
No, quella si chiama teoretica. È sotto la finestra, se minimizzi la finestra è nascosta.
Grazie. Sexy. Secondo investigare. Una investigare. Bro? Sì, come fare un bel chat. No, perché
Sei intellettualmente onesto, perché non condivido le tue idee. Non riesco a dire. Però dice, quando dicevo tutto la fisica box based, specializzando in questo, su quelle cose in realtà ci dire tutto significa. Cose che in realtà però non sono quindi c'è questa no, lui dice dice proprio che la roba là, che cosa che si trova in dei livelli esterni, si pagano, delle problematiche, però quindi dice che questo studio che fa però già le regole e questo studio come diceva che non deve essere quello del studio perché non può parlare di livelli di stare di cose poi ci siamo ritrovati a lavorare con questo significativamente diverso come l'articolo che dicevo delle varie quindi lui dice che gli stati da utilizzare nel sistema del laboratorio sono quelli mentre quelli del sistema e la dimensione lavorativa di dire ok, se tu lavori in questo qua, io non avevo bisogno di questi. Però questo veramente non funziona una cosa da fare infatti l'articolo di questo luogo che io vado a costruire di queste sono che fatto di l'azienda attuale. Quindi abbiamo passato da questo lavoro qua che adesso sono collegati di stare in salute. Possiamo dire che anche se poi la situazione che quello poi non riusciamo a fare così, quindi altri voti possiamo dire che quindi sono uguali, siamo sempre però quasi noi proprio, secondo me mettiamo la civile adesso come sbarcare, il giorno successivo e si sbarcare, no? Quello che fa, come quando si dice che gli stati bassi, quella la gente da trovare, quindi si può pure vedere. Quindi sono di questo tipo e proprio poi abbiamo le ultime slide quindi abbiamo dire le situazioni abbiamo no, sono quelli che tanto mi sono sempre questo mi sta praticamente quella di dato che due basi e ti dice praticamente i turni di salute ovviamente è un condensato di particelle di distanze quindi praticamente in varie giorni di due gruppi come si dice negli ultimi 4 anni c'è solo una versione non sono segretario che ti passa dopo fatto che quello che sono stati, quello che hanno scopo di sostanza, quello sono in stato. La funzione di cosa più le reti delle aziende come ora che sono stati, la volta la situazione per le direttive che ci e quando si va a riflettere su questo gioco, non si vede di gestire la politica. Questo punto di considerare questo gioco di spazi un po' più perché c'è anche il consiglio di ambito dove sto abitando, cioè c'erano delle cose un po' di più di partigiani che ti vedono prodotti di scrittori a masse diverse, non sono nel serio. Quindi tu sai il prezzo di rotazione che ti vende le cose alimentari, quindi questo futuro che ti dà l'automaticità, che non è nulla. Questo è una cosa quella che è responsabile del sicuro di mente. Dopo per esempio, sono stato, sono stato di se tu più che si prende di euro, di tutto, stato, quindi non sviluppato questo, i vari attuanze che si quindi magari sono quello che prendono poi sia semplice questione di spazio della valutazione. Quindi le cambi devi scegliere come è più già se non è concettuale, nel senso che tu poi trai una posizione di fatto, cioè prima era la posizione dopo. Però questo che fa, tipo, bisogno di il sistema e la valorizzazione di quello analizzare, quindi descrive un certo dopo, se hai questo sistema che sembra facendo magari sì, però tu hai due cose hai due figli che sono no, è questo è nella situazione in cui hai sì, quello se non vedi con l'analogia di prima sei così e prima sei così, cioè si già nelle cose in cui la lavorazione di variante però se tu pensi nel senso che il quindi la differenza tra le due parti perché se tu sei già solo nei casi